Hi and welcome to the lesson of real analysis. And today's class we are going to discuss some important topics that are left in the previous classes. So one of the important tests for the convergence of a sequence is a ratio test for the sequences. So we talked about the squeeze theorems, comparison test, and then now we are going to talk about this ratio test, and we'll see and we'll work on some problems to see how this works. So the theorem says that if an is a sequence of real numbers such that limit n tends to infinity, an plus 1 over an in the absolute value of this is equals to some limit L, and that limit L is less than 1, then an converges, right? So now, what does it mean actually is that if we are given a sequence, for instance, say that we are given 1 over n, then an plus 1 is obviously going to be 1 over n plus 1, and we are going to test this in the way that we have to apply the limit and in the absolute value of this an plus 1 over an, and we have to check whether this is less than 1 or not. So we can see here that this n goes to this n goes to the top, and it's now we can see that n over n times 1 plus 1 over n, which means this n and n cancels, and we are left with 1 over 1 plus n, which by application of limit we are going to get that is equals to 1 when the limit is applied and tend to infinity. But the theorem says that this limit that we get here should be strictly less than 1. Otherwise, if it's equal to 1, then the test is inconclusive. And if it's greater than 1, then the series is divergent. So in this case, our limit is 1. We get this L as 1, so we cannot conclude that the sequence is convergent or divergent by using this specific test. So we have other tests for these kind of sequences, so we can apply those tests, right? Now we will see here with an example that we can apply this ratio test, and we will take some more examples to gain the concept of the application of this ratio test. Now see here, we are given with a sequence that c power n over n factorial equals 0, where c is any real number, c belongs to the real number, and n we already know that this belongs to the natural numbers. So now we can apply the ratio test. We know that we have to do limit n tends to infinity an plus 1 over an, and we have to check this absolute value that should be less than 1. All right, so now on the application of this ratio test, we can write here that c power n plus 1 divided by n plus 1 factorial, and then whole divided by an, that is c power n over n factorial. So now I can manipulate this stuff here, and I can take this to the product here like this by taking the reciprocal. So it will be c power n plus 1 over n plus 1 factorial times n factorial over c power n. Then for this n plus 1 factorial, I can write that this is n times n plus 1 factorial. This can be written as n plus 1 times n factorial, because you know that the factorial n factorial equals to n times n minus 1 times n minus 2 and so on. All right, so we can write n plus 1 factorial equals to n plus 1 times n factorial. So this c power n plus 1 can also be written as c power n times c. Okay, so the bases are the same, as power will be added So it will be c to the power n, that will be cancelled with the c to the power n. This n factorial will be cancelled with n factorial, and we are going to be left with c over n plus 1, which implies that now we have a real number in the numerator and a natural number in the denominator, that is n plus 1. And by the Archimedean property, we already know that every time if we have a real number, then we have a natural number that exists that is greater than that real number. So it means that this n plus 1 is always going to be greater than this c. And whenever we are going to apply the limit, so limit goes inside, we know that the application of the limit will be like this: limit n tends to infinity, so it will be c over limit n tends to infinity times n plus 1. So as this goes to infinity, so the denominator goes to infinity, so c over 0 is going to be 0, which means that this is less than 1. So it's equals to 0 means this is less than 1, which implies that the ratio test is completed and it's suggests that the sequence converges, right? So this is the way to work in the case of these kind of some sequences. And you can also work on some examples from the books. It's very easy test, and you can see that whether the sequence converges or diverges, and it's very important as well. Now we are going to talk about the monotone sequences, very important topic again. So monotone sequences are of these kinds, that is monotone increasing, which means that if for all n belongs to n, if the number that is an is less than equals to an plus 1, then we say that this is monotone increasing sequence. For instance, if I have this sequence 1 2 3 4 5, this is a monotone increasing sequence, as we can see that 1 is less than 2, 2 is less than 3, 3 is less than 4. So every term is less than its successor. So it's called monotone increasing, and it can also be equal, like this constant sequence, because its equality sign also here, it's with the in less than and equals to. So this is also monotone increasing sequence, right? So this is monotone increasing because every term an equals an plus 1 equals an plus 2. So this is also monotone increasing sequence. And again, if we have a monotone decreasing sequence, so it's an is greater than equals to an plus 1. Let's suppose this sequence, then we can see that every term is less than its predecessor. So 1 is greater than 1 over 2, and 1 over 2 is greater than 1 over 3. So it's a monotone decreasing sequence. And a constant sequence, if we take like 1 1 1, we can also say that this is monotone decreasing sequence, or we can say it's monotone increasing. Both are fine, or we can generally say that it's a monotone sequence. For constant sequences, we can say that it's a monotone sequences. So regardless of saying that decreasing or increasing, we can just say that it's a monotone sequence. All right, then we have strictly increasing sequences. So the term strictly suggests that this an should be now strictly less than an plus 1. In this case, we discussed like this case. Here we have the strictly decreasing case, and every term is less than its successor. So it's strictly increasing. And for strictly decreasing, again, we have an is strictly greater than an plus 1. As in this case, we can see that every successor is less than its predecessor, right? And then we have monotone if it's any one of the above. So you say it's a monotone, right? Then we have some general rules for uh, checking that the sequence is monotone or not. Number one is that by subtracting successive terms, show that for all n belongs to n, this an plus 1 minus an is greater than or equals to 0, right? So by applying this rule, we can check whether the given sequence is monotone or not. And then we have the second rule: if all an are positive, divide successive terms and show that this ratio n plus 1 over an is greater than equals to 1, right? And then we have if f of x equals to x, if we have some function like this is differentiable, show that for all x greater than equals to 1, the derivative is greater than equals to 0. So again, we can use this as well, and or we can use a mathematical induction to show that for all n belongs to n, the an is less than equals to an plus 1. So these are the four methods, and we will see in some problems, we will work out some of them, and we'll see how to apply these methods. So for instance, in this example, we are given with this sequence, that is an equals to 1 over n. Now by applying the rule 1, that we are going to show that an minus an plus 1 is less than equals to 0, as in the rule 1 they said this rule, that an plus 1 minus an is greater than equals to 0. So subtracting the successive terms, so it's not like this actually. So now we have an equals to 1 over n, and an plus 1 is obviously 1 over n plus 1. Then by an plus 1 minus an, we can see that this will be 1 over n plus 1 minus 1 over n. So by taking the LCM and by simplifying the equation, we have n minus n. This n cancels. We are left with negative 1 over n squared plus n, which suggests that this thing is always positive here because these are natural numbers. And this negative 1 suggests that now this whole term will always be negative, which implies that this will always be less than 0. So which means that this is strictly decreasing, because this term is an plus 1 minus an is less than 0. So it's a strictly decreasing sequence, right? And then we have another example, that is 3n over 4n plus 5 is strictly increasing. So we have to show that this is strictly increasing. So now we are going to use the rule number 2, and we are going to show that this rule is greater than or lesser than 1. And then we can just develop the argument that it's increasing or decreasing. So we have an plus 1. So an plus 1 for this sequence is going to be simply 3 times n plus 1. So put n plus 1 everywhere for n, and simplify the equation, multiplied by, okay, here I'm multiplying by taking the reciprocal of this an. You can just I'm excluding one step, and I have written here directly. So I can write it here that 3 times n plus 1 over 4 times n plus 1 plus 5 whole divided by 3n over 4n plus 5. So this whole thing I can write in this way also, right? So now we can simplify this, and on simplification, simply it's simple algebra, and on simplification we get 1 plus 15 over this whole thing. So these are the natural numbers, so this whole thing is going to be positive, and here we have 1 plus some number here, 15 over 12n squared plus 27, and so it's always going to be greater than 1, which means that it's increasing. And if it's lesser than 1, then we can say that it's decreasing, but it suggests here that it's greater than 1, which means that this is increasing sequence, right? And now we have one more example, that 3 power n over n cubed is strictly increasing after first 3 terms. So now after first 3 terms means that this is going to be strictly increasing after first 3 terms. So the first 3 terms might be increasing or decreasing. We are not, we don't bother about the first 3 terms. We can see after first 3 terms. So applying the rule that, so first of all, this an plus 1 will be 3 to the power n plus 1 over n plus 1 cubed. All right, so this we can write in this way. And then we have 3 to the power, and we can break this into 3 to the power n times 3. So this and this cancels. We are left with 3n cube over n plus 1 cube. So 3n cube over n plus 1 cube is greater than 1 for all n greater than equals to 3. And we can check here by applying, let's say we are applying 4, n equals to 4. So it will be 4 plus 1 cube. And we can check that this number is going to be greater than 1. So 4 cube is 64, and 64 times 3 is 64 times 3. We can check that it's 192, and 4 plus 1 5 cube is 125. So you can see that uh, this will be 192 over 125, which is greater than 1. And we can check for every value. So this is greater than 1, which means that this is strictly increasing after the first 3 terms. Okay, now monotone convergence theorem says that every bounded monotone sequence converges. Okay, if we have a sequence that is monotone, it's either monotone increasing or monotone decreasing, and it's bounded, then we can say that the sequence converge. So if an is a monotone increasing sequence that is bounded above, like we can say that we have a sequence, for instance, -1 over n. This is equals to -1, then -1 over 2, -1 over 3, and so on. So we can see that this is a monotone increasing sequence because every term uh, is every successor is greater than the predecessor, right? So like we can say that -1 is less than -half, -half is less than -1 over 3 because of this negative sign. So this is less than 1 over 3, and so on. And it's the sequence is going towards 0 here. So the maximum value of this sequence, not maximum value of the sequence, but the supremum of the sequence is going to be 0. That is the supremum of the sequence. So an is monotone increasing sequence that is bounded above, and it's bounded above because it eventually goes to 0. So it's bounded above because the infimum is -1. The least value of the sequence is the least greatest lower bound, that is GLB, is -1, and the greatest least upper bound is 0. So this is bounded above and bounded below as well, but it's bounded above is enough for us. Then limit n tends to infinity an equals to supremum an. So the limit is going to be equal to the supremum. Like in this case, that limit n tends to infinity, the supremum of the sequence. Okay, first of all, the supremum is 0, you know that. And again, the limit n tends to infinity, -1 over n, is also equals to 0. So which means that the supremum and the limit are equal. That is what this condition is saying, right? So whatever the supremum is will be the limit of the sequence if it's a monotone increasing sequence that is bounded above. And if an is monotone decreasing sequence that is bounded below, then the limit n tends to infinity an is infimum an. For instance, take in this case, we have 1, 1 over 2, 1 over 3. We know that this is a monotone decreasing sequence. And the infimum of this sequence is going to be 0 because the sequence converges to 0. We know that. And then the limit n tends to infinity an is also going to be 0. So we check that in these two cases, we have two examples, very simple examples, that the limit and supremum and limit and infimum are equal in the cases. Uh, like in this case, monotone increasing case, the sequence is bounded, then the limit is equals to supremum. And for the monotone decreasing case, the limit is equals to the infimum. Now we have to prove that in general. We cannot prove by examples, but we have to prove in general. So suppose that an is bounded and monotone increasing sequence. Since an is bounded above, then an has upper bounds. We know that, yes, it's a bounded sequence, then it has upper bound. It must have upper bound because of the completeness property of R. So there exists supremum an. We can say that this U is the supremum of an. Now we are claiming that there is an element U that is a supremum of this set. Now by the epsilon criteria for supremum, we have the epsilon criteria that says there exists n naught belongs to n such that this number a n naught of the sequence will be greater than the u minus epsilon. Okay, so by the epsilon criterion, what does it mean? That if we have a number here, for instance, we have a number somewhere here, there is a and naught, and we have the supremum somewhere here, like that, somewhere here u, and if I subtract some a small number epsilon from this u, then this number is going to be greater, because if I subtract an epsilon from this u, then this u minus epsilon will be somewhere here. All right, so now this number is going to be greater. This is, we can write, is positive, sorry, it's negative infinity to positive infinity. So now if my number that is u minus epsilon comes here, which means that now this a n naught is greater than u minus epsilon, because it's this u minus epsilon is behind this a n naught, right? So this a n naught is such close to this supremum u, which means that if I subtract any small number epsilon from u, then my a n naught is going to be greater, right? So this element a n naught is going to be greater if I subtract some epsilon from this u, my supremum. But an is monotone increasing sequence. We know that it's given in the condition, which means that n is greater than or equals to n naught, right? Because we know that as if we have some a n naught here, some number a n naught here, so an, which will be greater than this a n naught, because for monotone increasing sequences, we know that an is less than an plus 1, is less than an plus 2, and so on. And in the definition of the convergence, we say that for all n belongs to naturals such that n is greater than equals to n naught, right? So when n is greater than equals to n naught, it means that n is some element after n naught. So in the case of the monotone increasing sequences, the element that is the successor element is always greater. So this an will be greater, right? Thus an is greater than equals to an naught, so it's also greater than u minus epsilon, right? So if my an naught is somewhere here, and my u is somewhere here, then my an is going to be somewhere here. And if u minus epsilon that was here, for instance, u minus epsilon that was here, so it was less than an naught, so eventually it's going to be less than an as well, right? So an is greater than u minus epsilon. Since u is the supremum, so an should be less than equals to u. Yes, because every element is less than or equals to its supremum for increasing bounded sequence. We know that. So mm, like we discussed in the example -1 over n, so it's a monotone increasing sequence, and this is starting from -1 and going towards 0, and we know that every element is less than its successor, like -1 is less than -half, this is less than -1 over 3, less than so on, and every element will be less than 0, right? So here we write an is less than equals to u for all n belongs to n. Therefore, for n greater than equals to n naught implies, by definition, this is the definition of the convergence, implies that u minus epsilon is less than an. All right, we already discussed. That is less than equals to u, okay, because every element of the set is less than or equals to its supremum. And for u, we know that u is less than u plus e. It's obvious if we have some u here, right? And then we have obviously u plus epsilon here, which is greater than u. So u is less than u plus epsilon. It's very obvious. So now we construct this argument here. U minus epsilon is less than an, is less than equals to u, is less than u plus epsilon. Now we remove this u, we don't need this u. We can just take these three elements to generalize the argument and complete the argument. So an is bounded between u minus epsilon and u plus epsilon, which means that an minus u is bounded between negative and positive epsilon. Then by the rule of the inequality, I can just use this mod and write an minus u is less than epsilon, which means that limit, which is the definition that limit n tends to infinity, an equals to u, which is the supremum of the sequence, right? So this way we can prove this, and we can also prove the other argument that for monotone decreasing sequences, limit is equals to the infimum by the similar argument, by the same arguments, just going in the other direction. Okay, so this is all for the class, and in the next class I'm going to talk about some more sequences, divergent sequences especially, and we'll take some examples on the divergent sequences. So that's all for the time being for today. Thanks for watching the lesson.